Hello students, today I will take the topic pulse width modulation. I will discuss the importance of pulse width modulation and giving you the overview that what we will do regarding pulse width modulation. So we'll understand that what is pulse width modulation first, then its importance and how does actually it functions, and then how actually with the help of timers. Already we have studied timers, so it is important to remember the concept of timers to understand pulse width modulation. If you are not thorough with the understanding of timers, it would be difficult for you to understand pulse width modulation because exactly the same registers, not exactly the same means, but the idea of using the registers, their context would exactly be the same. And then later on, we will understand the types of pulse width modulated signals, single-edged, double-edged, or also known as centrally aligned. So along with this, obviously, we're going to use certain registers. So then we will understand different registers and their importance. And later on, to understand the concept better, we will go through two programs which we do require for our lab, and that we will understand through those two programs. The first program is that will generate one pulse width modulated signal to control the brightness of LED. There is a separate PWM module in our kit. I will show that thing in our lecture. So where is that? So you have to connect that module with your CNA A, B, C, D, depending on which pin you would use as PWM pin. So based on that, you would generate the modulated signal, and that modulated signal would control the brightness of that LED. That we will understand. And then exactly on the same lines, we have to adjust the brightness of that LED, but this time we will introduce one more element to it. So that element is the keyboard. So based on the switch which you will press in your keyboard, so that would determine the brightness level of that LED. So more or less the program would remain same, but just the one keyboard element we will add. So if we will press switch corresponds to row 1, column 1, so brightness level would be somewhat like suppose X. If you will press row 1, column 2, so brightness level would be Y. So depending on whatever switch you will press, you would notice different kind of brightness corresponding to that LED. So that is all about which we have to study. So first we'll understand what is pulse width modulation. You all are aware about the modulation concept. So modulation is just to vary some element. So as we know, amplitude modulation where you change the amplitude of a signal. Frequency modulation where we'll change and varies the frequency of a signal. Likewise here, we will modulate the pulse width. To understand the pulse width or pulse width modulation, we'll first understand it through this diagram. So here, as you can see in one cycle, for 25% of the time, your signal is high, that is plus 5 volt. Your signal is high for 25% of the time. And for 75% of the time, signal is low. Understand it? So in this way, we can also calculate the duty cycle. So duty cycle is nothing but out of whole time duration or one cycle. In proportion to that, for how long the signal was high, that determines the duty cycle of that signal. You can vary this width. You can vary this width in one cycle. So here in this example, it is 25% of the time. That is the width of a signal which was high for 25% of the time. In next case, it is 50% of the time. So you have modulated, you have varied the width of a signal. So you are varying the duty cycle. So in another way, we can say also that if you will change the duty cycle, you are changing the width of a signal. That in typical sense, uh, modulating the width of a signal. So for that long, if the duty cycle is 75%, that means 75% of the total cycle time, your signal will remain high, that is +5. And here, this is +5 means high voltage and 0 is low voltage. So typically it is so, the +5 or 0, but it is not necessary. So if we have to generalize it, +5 volt may be anything. So we may consider it as a high voltage plus V. And likewise, here in this example, it is 0 voltage, but it may be possible that it may be minus V. V may vary. Now, if you have to average out the voltage, because that's where the importance of these signals lies, because they will give you, so they will give you what? They will give you the average voltage. So how you can calculate the average voltage? So for how long, in one cycle duration, for how long your signal was at higher voltage and for how long your signal was at lower voltage, you just sum it up. That will give you the average voltage. So in this example, if for 50% of the time it was +5 voltage, and for the next it was 0, so 0 will not add to the average voltage. So we will get some voltage out that there. That will be the average voltage. So where actually these signals may be important or these signals can be used, because these signals over a period of time, if you will keep on generating, they will give you or imitate the analog signal. So through digital source, because our kit or our ARM processor could only provide +5 voltage or 0 voltage. It can't vary in between. And not even +5, it is 3.3 voltage. It works with 3.3 voltage. So that is immaterial to understand the pulse width modulation. The idea is that some higher voltage it can generate or the lower voltage. In between, it can't generate anything. So the binary values, so in binary values, either 1 or 0, it can generate. Then if you have to imitate the analog signal, so in that situation, you have to fluctuate that plus V and minus V over a period of time with higher frequency. So if you can increase the frequency rate, it may imitate the analog signal. So these are used, pulse width modulation signals are used to imitate the analog signals. And how to calculate the average. So let's suppose there is an example that if we have to generate a 3 voltage signal, so +5 voltage is the higher voltage and 0 is the lower voltage. So how long you have to keep +5 voltage out of one duration, that is plus 5 volt multiplied by 0.6 will give you 3 voltage. So in that situation, your duty cycle need to be 60%. So 60% of the total duration, you have to keep your signal as +5 voltage. Then it will give you an average voltage of 3 voltage. If you will increase it to 80% of the time, then it will yield 4 voltage. So that's how we can average out. So where exactly we can use this concept and this average voltage, where can we feed in and control several things. So let's see where can we use these things. So we can use the pulse width modulation concept to control motion. So we can control the brightness of screen, we can control the brightness of LEDs, we can encode analog signals into its digital form, we can regulate the power. So in several situations, so where you have to control the voltage, the average voltage, where you have to control, there we can use our LPC1768 or any ARM processor or any processor that would generate the modulated signal, width modulated signal, and that would later on maybe used to feed into some analog device, because if you will keep recurring that signal plus higher voltage, lower voltage, and with higher frequency, you would do so, then it would imitate the analog signal. So in this way, we can generate the analog signal. So that is one part of our understanding. Now we will understand that how exactly we can generate these modulated signals. To understand that, we'll go here. So if you can see, I will zoom in. So here is our clock. So I'm briefing you about how to generate the modulated signal over a pin. So to understand this much better, with respect to LPC1768 kit, so 6 pins are there. So those are well-defined pins. Over those pins, pulse width modulated signals can be generated. So those pins are, so 6 signals you can generate at a time. You can generate 6 signals at a time. So 6 channels are possible at a time. You can generate 6 signals, pulse width modulated signal, and these pins are well defined. So over port number 2, pin number 0, pin number 1, pin number 2, pin number 3, pin number 4, pin number 5 of port number 2, we can generate the pulse width modulated signal. And the function is second function. So function 1 is for GPIO, as we all know. So if we have to use any one of these pins as pulse width modulated, then in the corresponding pin select register, so here it is pin port number 2.0. So obviously we'll use I think pin select 4 we will use. So it is .0. So 0 and first bit would require to have the value 0, 1, make it function as the pulse width modulating pin. So this concept, you know, that how to configure any pin with a corresponding or a particular function. So here only 6 pins are possible, and that would come from port number 2, pin number 0 to 5. So only these pins we can use. So corresponding pin based on which channel, which PWM channel you want to use, you have to configure the corresponding pin as PWM pin. We will understand match registers later on. What is the importance of these match registers? So once we will understand the register set, which would come along with PWM module, which would make it more functional. So before that, I want to brief you about how to actually generate signals. Later on, those things will make more sense. So suppose here we have a clock. So it's a clock period. So it is generating its own signals. And as and when one clock ends its cycle, means after every cycle, every clock period time, we're updating our counter. So there is one counter which we are updating after every clock time. So we have pre-decided it that we will increment it till 6. So somewhere 6 value is written and we'll keep on incrementing our counter, and always when we are incrementing we will check, we'll match it with that match register value, that whether the value is 6 or not. So here it is predefined. We have already predefined it that we will always increase our counter till 6. The moment it reaches 6, then we will reset it. We will once again make it 0. So if you can relate it with TC or match registers, if you have any idea about timers, you can very well relate that we will increment our counter in TC value. So we'll increment our TC time counter, and we will reach till 6. And we will always, once we will increment it, we will always check it against any match register. So there are several match registers. So in detail, I will go later on, but there is one match register. We will always check it. Okay, so that is one thing. Now, the good part is that once you are incrementing your counter, at that time there is pin, and over that pin, either we can have a value plus 5 volt, or either we can have a value 0. So to make it more generalized, some positive voltage we want to give to that pin, which we are using as pulse width modulating uh, pin already, which we have configured. So over that pin, either the value could be positive voltage or either the value could be negative voltage. So we will use plus 5 volt and 0 volt for our understanding. So suppose those two values are possible. Now we will go about with certain decision parameter. And what is our decision parameter? The parameter is that if our counter value is less than equal to 3, then we will put higher voltage over our pin. Or once our counter increases beyond 3, once the value goes beyond 3, then we will put minus V or 0 voltage. It is so simple. In this way, we can generate the signal and we can modulate the band, means width. How we can modulate the width? We have to keep the value. Suppose here the value was 3. So we have decided that once the counter reaches 3, then means once the counter reaches beyond 3, then we will make our signal 0. Prior to that, our signal would remain high. So in this way, when it is going to be high, based on the value 3, the 3 we can vary. 3 can be 2, 3 can be 4, 3 can be 5, 3 can be 6, 3 can be 1, 3 can be anything. So we also require one more register which will keep this value. So we will always check our counter value against that value. If that value, our timer counter TC value or our counter value is less than that value which we have pre-decided. So in this case, the value which we have decided was 3. So if that value would remain be less than our counter value, means our counter value would remain be less than whatever we have decided. In this case, it was 3. Then we will make our signal high. Otherwise, we will make our signal low. In this way, we can vary our width of a signal, because then we have to just change that value. So here it is decided 3, next time we can decide 4, next time we can decide 2, based on our requirement of average voltage, whatever the average voltage we require. Now to understand the duty cycle in this example, because total how many cycles are there? 7 cycles are there. The signal period is total signal period comprises of 7 clock cycles. Out of 7 clock cycles, our signal was high for 4 durations, for 4 clock cycles. So duty cycle is 4 by 7. In percentage, you can write 4 by 7 into 100. Now, as you can see, the leading edge and trailing edge. So depending on which edge you would vary, then even there's a bifurcation in single edge to pulse width modulation. So prior to understand single edged or double edged means there is a bifurcation, there's a division in pulse width modulation signal. So one part is single edged. Within single edge there is a bifurcation, that is left aligned or right aligned, and there is then one more category to it that is separate, that is centrally aligned or double edged. So what is central aligned or double edged, and what is single edged? So this is the example of single edged. So here the leading edge and the trailing edge, how we decide? Because here in our example, leading edge is fixed. So always the leading edge would start from 0. So when your value is 0, so your leading edge will position it right against the 0 counter value. Here you can see. And based on whatever value you would decide, in this example it is 3. If you will decide 4, then you can modulate your trailing edge. So then your trailing edge would start from 4. If the value is 5, you can extend the trailing edge till 5, and then the trailing edge would come into picture. So in this way you are varying the trailing edge. So this is called left aligned, because your leading edge, the left edge is aligned, that is called left aligned. Reverse of it, in contrast, if you will vary the leading edge and you will always fix the trailing edge, which is very well possible. How that is possible? Suppose instead of here our argument was that if your value is less than 3 or equal to 3, then you will always start with high signal. You may start with 0 also. If you will start with 0, and once your value will go over 3, then you will make your signal high. So in this way, always you will fix your right side, or then it would be right aligned. Always you will fix your trailing edge. So that is an example of right align. This is, so it depends on that how you will decide to your high voltage or low voltage, when to keep the voltage high over the pin, when to keep the voltage low over the pin. That is example corresponding to single edged. In single edged, 2 bifurcations were there, left aligned and right aligned. Then comes centrally aligned. So in centrally aligned, we'll see the centrally aligned. So this is an example of centrally aligned. Here you require means a clock obviously, and the counter you require. Here you will increment the counter first. So you have incremented it till 6. Then instead of making it 0, you will start decrementing the counter, 6, 5, 4, 3, 2, 1 and 0. And you will apply the logic, and the logic says that if your value is less than or equal to 3, then you will keep your pin at lower voltage, or if your value is beyond 3 always, then you will keep your pin value at 1. So in this way, nicely, it will come as a centrally aligned. Your signal would be centrally aligned. It is aligned to the sixth counter value. So that is called centrally aligned, or because both leading and trailing edge you can vary based on whatever the value you will choose. Because on left side you can choose one value, on right side you can choose another value. So based on that, you could have a variation in width, and that variation uh, would be on account of both leading edge and trailing edge. That's why it is called centrally aligned or double-edged. Here, if we have to calculate the duty cycle, so out of 12 cycles, so it has complete 12 cycles. If you have to calculate the period of this signal uh, with respect to clock, so clock has certain duration or the clock period. So 12 into clock period, so because total value, total number of clocks are 12 in numbers. And what about the duty cycle? Because our signal is high for a duration of 5 clock cycles out of the total 12 cycles. So that's why it is 5 divided by 12, and percentage 5 divided by 12 into 100. So hope you might be able to grasp the concept behind single-edged and double-edged. If we will understand the signal period of our single-edged, so here the single-edged based on the maximum counter value 6, so it is 6 plus 1 into clock period. Whereas if you would go to the centrally aligned, it is just the double of that, and so 12 into clock period. So in this way, based on whatever the value you will choose, you can vary the duty cycles, you can vary the signal periods. So in a way, you can vary the frequency of the channels. Because period is equal to 1 divided by frequency, you can vary the frequency. If you have to vary the frequency, you can change the periods and all. This understanding you require to understand now the register sets, that why do we have those register sets, which now I will bring for your understanding. So first, it is all about configuring a particular pin as pulse width modulation. So total, we have only one module. So PWM1, only one module we have in our LPC 1768, only one pulse width modulation, but 6 channels you can use. So at a time you can generate 6 pulse width modulated signals, and corresponding to each channel, we have an associated pin. That pin first we have to configure as pulse width modulated pin, and for that the function is first function. So correspondingly, so here we are using the port number 2, pin number 0. So obviously for pin number 0, 0 and first bit of pin select 4 we would use to configure as pulse width modulated output pin, and we will write value 0, 1 for that matter. Likewise for second pin, second channel, third channel, fourth channel, fifth channel, sixth channel. Now corresponding to each channel, we have corresponding match register. So if we are using match register, means channel 1, so then we have to use the match register 1. This match register would contain that value. which your counter would always match with, that whether the value is less than that value or not. If it is less than that value or less than or equal to that value, then the pin will go high, otherwise the pin will be low. So that value we have to write in the corresponding match register. So in total, 7 match registers are there. 6 match registers we will use for 6 channels. One match register MR0 with name MR0 we will use for writing to it the total duration of our signal. In previous case, so if I will relate this with our previous case, so what we will write in, suppose if we are using the first channel as a pulse width modulation. So first we will configure the pin select 4 register. We will write over the bits 0 and 1 as 0 1 because it is a function 1. So 1 we have to write over these 2 bits. Then in that example, our value was 3. So we were matching our counter against the value 3. So in MR1 register, we will write the value 3. Each time, whenever timer will increment its value, it will always check whether it is less than 3 or greater than 3. If it is less than 3 or equal to 3, then the signal will go as a high, or later on after that, the signal will be low. Now it has to stop this. Now it has to stop and restart. So how long that process will be there? So somewhere you have to write that value. So what is the duration of complete cycle that you have to write? It's complete pulse width modulation cycle. The cycle time you have to write somewhere. So here in our previous example, the time was 6. So counter will start from 0 and it will go till 6. So that 6 value we have to write in MR0. So MR0 will hold the complete duration time, the clock cycle time. Means not clock cycle, the complete pulse width modulation time. So that time it will hold. So with that example, it would be much easier to understand. So MR1 will hold the value 3 and MR0 will hold the value 6. Once counter will reach the 6 value, then the function would be that it will have to repeat the same process. Then PC will be reset, PC will be 0, means the counter value will be 0. Once again it will start. So once the value of counter value is 0, it will once again match it with MR1. So MR1 value is 3. So it is 0 is less than 3. So pin would go as high, and it will increment to 1. It will match with 3. Pin will go as high, then the value is 2. Pin will go as high, the value is 3. Pin will go as high. The moment it will reach the 4 value, then obviously 4 is greater than 3. Then as per our understanding, then the value should be 0. So system or our processor will make it as 0. The pin value will be 0 or minus V value or voltage, whatever convention you would use for that matter. So in this way, and once 4, so counter value is 4, so it is 0 value, then 5, it is still greater than but less than that 6 value. Once it will become 6 minus means 0 value, but once it reaches 6, then it has to reset it. So PC will become 0, and once again the same process will restart. So that is the overall working concept of pulse width modulation if you are using single edged. If you will use double edge or centrally aligned instead of 2 registers, so here it gives you a functionality over LPC1768 gives you a functionality where you can generate 6 parallel single-edged signals, pulse width modulated signals. Whereas if you have to generate double, then you have to club 2 registers. So because one for left edge, another one for right edge. So in example, if you could relate, so either you can vary the left edge or you can vary the right edge, means the rising edge or the trailing edge. You can vary both the edge. So to vary both the edge, you require two match registers. So for that matter, two registers would account for single, double edge or centrally aligned signal. So at a time, you can generate only three double edge signals. Whereas if you will go for a single edged, then you can generate in parallel six signals. Then now we will understand the pulse width modulation registers. If you have gone through the timer, this is going to be so easy because all the registers, though this module has its separate registers, but the context in which we will use those registers would exactly be the same. So how we have used TC, PC, PR, match registers, TCR registers, CTCR registers, so many registers were there in timers. So exactly using the same concept, we will generate the signal. We'll use the timer concept, but register names are different. Though their context in which we will use would remain the same, but timer registers are separate and pulse width modulation registers are separate. Even their names are separate. And but to understand pulse width modulation registers, if you would have already understood timer registers, it would be much easier because the context in which we will use or the working principle behind each register remains same. Now, first one is interrupt registers. So as in case of timers, we have already seen. So interrupt register. So once you have already matched, so your timer value, TC value, with certain match register value. Now you have three possibilities. Either you can take interrupt. So if you have to take interrupt, so in interrupt register, you have to write a logic 1 to clear the corresponding interrupt or to acknowledge it. So that is the interrupt register, working of the interrupt register. So next one is PCR register. Already, if you have understood timer, so in timer, we were using only initial 2-bit positions in TCR register. First one is to enable TC and PC. Second position, the first position means 0th position we have used to enable or disable it. And first position we have used for resetting purpose, to reset TC and PC in sync. So both will become 0 if you will make that reset bit as 1. Exactly the same functionality we will use here also, with one more addition to enable. So some third bit we will use in TCR register to enable our pulse width modulation module. So to enable those pins, so that our system would understand that these pins can use for uh, signals. So we will use the third bit position for that purpose. Other bits are reserved. Then time count, TC counter, you know the understanding of TC. Exactly, it is used for the same purpose. So you will increment TC here also after PR plus 1 cycles. So if you can't understand it here, those who can't understand that what is the functionality or the relationship between TC, PC and PR. So once again, I'm briefing you about that. So PR is one pre-scale register where you will put some value. That value we have to calculate initially depending on what resolution we want for our timer. So when I'm using the word resolution, that means in normal understanding, that after how long, after how much time you want to increment the TC value. So based on that, that is called time resolution time. Based on that, you have to calculate the pre-scale value. That depends on clock frequency, which clock frequency you will use, and that also depends on whether PCLK is equal to CCLK or CCLK by 2, by 8, by 4. It all depends on that. Now in between there is one more register, PC register. PC register will increment its value after completion of each PCLK clock cycle time. Once you will increment PC value, we will always check that value against PR value. Once both value will become equal, at that time in the next cycle of PCLK, we will increment our TC value, and at that time we also make our PC value 0, means it has to once again repeat the same process. So PC value will keep on incrementing after every PCLK cycle, and always after that we will check it against the PR value. If both become equal, then we will make our PC value 0 because it has to once again do the same operation. And in the next PCLK cycle, we will increment our TC cycle. So TC we will increment after every PR plus 1 cycle time. So in this way, we can introduce certain delay in the increment of PC value. So already I have discussed about PR and PC value. Then you have match control register. Now after matching, there are several match registers. So here in our example, we have 7 match registers, 6 match registers starting from MR1 to MR6. We will use for matching against the timer TC value. And MR0 also we will use to match against TC value, but MR0 will hold spatial value. That is, MR0 will hold the cycle, the complete cycle period time in terms of ticks, number of ticks of TC. So that MR0 will hold. So what MR0 will hold already we have discussed. For the time duration for which your signal was on plus the time duration for which your signal was off in terms of TC ticks or TC increment or TC the counter value. MR1 and MR6 till MR1 means from MR1 till MR6. So these 6 match registers we will use to hold the value corresponding to the duty cycle. So suppose if MR0 is holding total value 6 and we want 50% of our duty cycle, then obviously MR1 should hold the value 3. So less than 3, your value will be, means your system would generate the signal 1 over that pin, otherwise it will keep the value low. So MR1 till MR6, these values will hold certain value depending on what kind of duty cycle, what value of the duty cycle we are expecting from that channel. So it depends on what output voltage in terms of average we want. Depending on that, we will keep the value. PCR value that is used to control the PWM. This is a PWM control register, so it is used to enable, disable the channels, and to select whether single edge we will select or double edge we will select. So for that purpose, we have PCR register, and there is one more register. This is interesting: load enable register. It will enable the use of new PWM value. So in between, suppose if we are using pulse width modulation first signal, first channel we are using. So corresponding to that, we have already decided one match value depending on the duty cycle, but we want to vary this duty cycle. So to vary that duty cycle, obviously you have to then reload some new value to that match register. Prior to reload, you have to enable that reloading through LER register. So until and unless you would enable it, you would not find the exact value. Because why is it so? Because all these match registers has their own shadow register. So whatever the value we initially put, that goes to shadow register. So in the next cycle, if you have to reload, the value would remain goes to the shadow registers. So same value would be there in the shadow register if you are not reloading it. But if you want to reload, so obviously you have to latch that value which is there in your match register to the shadow register also. So for that purpose, you have to enable the load so that it could be latched to the shadow register and later can be used in the next subsequent cycles. So that is the importance of load enable register. So here you can see the TCR register. It's a timer control register. So already if you have an understanding about timers, so first bit is for enabling the counter. If you have to enable the counter, you have to make this value 1, means this position as 1. Then if you have to reset the timer, reset means TC and PC would go to 0 in sync. Both will be 0 exactly the same time. So to reset it, then the value should be at this position should be 1. So, and then the second position is a reserve. And the third bit, this fourth bit in particular, but the position number 3rd, it will start from 0. This position is used to enable PWM. If you will not enable it, then obviously your timers would not help you in generating the signal. So to generate any of the signal, so it is not channel specific, it is module specific. So PWM module, to enable the PWM module in TCR register, 4th bit position should be, so should be 1. So that's about TCR register. And then you have a match control register. Now in match control register, we have 7 match registers. So, and whenever there would be a match, so system has 3 ways to deal with that match. So there are 3 possibilities system can work on. So first possibility is that it may leads to an interrupt. Second one is that after match, your system may reset the timer. Third possibility is that your system may stop there as it is, will do nothing. So these are the 3 possibilities after every match. So which your system would work on or would take as a step forward after every match. So because 7 match registers are there, 3 possibilities. So how you can encode that information for your system through MCR register, you require 21 bits, 7 3 21. 0th bit, first bit and second bit corresponds to match register 0. First bit, I mean 0, 1, 2, third, fourth, fifth, subsequent 3 for match register 1, subsequent 3 for match register 2, subsequent 3 for match register 3, and so on. So in this way, you would end up using initial 21 bits corresponding to all match registers. So that is the functionality corresponding to MCR register, match control register. And this is the naming convention, PWM match register. So which match register 0 to 6 and interrupt reset, and stop. This is exactly like as we have studied corresponding to timers. This is exactly the same functionality. Now, PCR to control the PWM module. So here the possibility is that which signal, which output pin you want to use as PWM. So you have 6 channels over which you can take the modulated signal. Now, which one out of 6 you want to use? So from 2 to 6, you have a choice. From 2 to 6, so you can select the corresponding, no, from 9 to 14. So from 9 to 14 is to enable or disable. So these 9 to 14, in 9 to 14, from 9 to 14. So 9, 10, 11, 12, 13, 14. So total 6 channels are there. Which one you want to enable? So corresponding to that bit position, you can write the value 1. So it would amount to select that pin as output pin, and you are enabling that channel. Already you have enabled using TCR the complete PWM module. So within that, if you want to enable particular channels, because 6 channels are there, you can enable it through mentioning one corresponding to uh, those channels. So from 1st to 6, so 9 to 14 bits. From 2 to 6, so from 2 to 6, this is corresponding to selecting the single edge and double edge mode, because in 2 modes you can generate the signals. Either you can generate the signal using single edged mode or double edge mode. So if you will mention corresponding to, so 2, 3, 4, 5, 6. So if you will mention it as 0, then it would amount to selecting that channel as single edge mode. If you would mention it as 1, then it would go into double edge mode. So that is about PCR register. Then already I have defined to LER register, because LER register, load enable register. So in between, if you want to vary the modulation, if you want to change the value of your match register based on that match register, because what you are mentioning in the match registers, the corresponding duty cycle, for how long your signal will go high and for how long your signal will be low. So that what you are mentioning through match registers. And in match register 0, you have mentioned the whole duration, for which the total time your signal would be high and your signal would be low. And in corresponding match registers, you have mentioned the corresponding time over which your signal would be high. So that is corresponding to the duty cycle. Now, because every value you once again means during the course of signal generation, you want to vary this duration. You want to vary the duration for which your signal would remain high or low. You want to modulate that signal over a period of time. So for that purpose, first you have to enable uh, the entry, the new value which could enter or which could find its place in the match registers. So if you want to change the value of current value to some new value in match registers, then prior to that, you have to enable it through LER, load enable registers. So we have 7 match registers. So corresponding to 7 match registers starting with 0 till 6. We have the position here in LER. First you have to make that position as 1, then only you can change the value in the corresponding match registers. That is the importance of LER register. And already I have defined the PWM working, so I don't need to explain it further. And already I have I mentioned about the shadow register. That's why, because whatever the value in the match register, first that match register value would find its place in the shadow register. So directly the shadow register would copy the value, and then your whole comparison would take place using the shadow register. So if you have to once again change the value in the match register, so that match register value should reflect in the shadow register. For that purpose, it should latch. Your match register should latch its value to the shadow register. For that purpose, you have to enable it through LDR register. So once again, I will explain it for you using this example. So suppose, I mean, your TC value is 20, 60. So suppose the match register value is 60. So match register value is 60. You can relate it with my previous example. The match register value at that time was 3. So here the match register value is 60. So if your TC value is less than 60, then your signal will always be high, or it may be equal, means equal to 60, your value will be high, or I mean any logic you can apply there. It would not make any difference in terms of generation of the signal. So if the value is 60, so obviously once you will increment the TC value, you would always compare that value TC value with 60, the match register value. If it is less, your system will always put higher voltage over the corresponding pin. So here it is one value. Once your value, once this value becomes, TC value becomes 60, then you have to come down. Then your signal would be 0 over the pin. And you will always compare it with 100 once, because 100 is the total duration. You have to always keep on checking the total duration, the total signal period. Once your TC reaches the value 100, at that time you have to switch it over again. So you have to make your TC value 0, your PC value 0, and once again start the same function. So it is so simple. So where your total cycle time is, it will always be there in MR0, and MR1 till MR6 will always hold to, the duty cycle corresponding to the PWM channel. So MR1 will hold to the duty cycle value corresponding to channel 1. MR2 will hold it for channel 2, MR3 for this, MR6 for channel 6. That's all. Now how to configure? So obviously you have to select the pins. So these are some steps which you will follow. First is, already I have mentioned, so these pins are there. Port number 2, pin number 0, 1, 2, 3, 4, 5. So we will use these pins for our modulated signal, and this corresponds to function number 1. So first we have to configure these pins as pulse width modulated output signal pins. So how we can configure, because we are using the port number 2, pin number 0 till 4, and so we have to use the pin select 4. In pin select 4, corresponding to those bit positions, we have to write the value 0, 1. That's how you can configure it. Once you have configured this value, then later on you have to configure the TCR register. In TCR register, what are all the values? You have to enable the PWM. So the fourth bit position you have to enable as 1. That is the second step, because you have to enable the PWM module. Until and unless you enable that module, you will not be able to capture the signals, or take the signals, output signals from the corresponding pin. Then, so first you have configured the selected pin. Once you have selected that pin as PWM pin, then you will enable it through register. Once you have enabled it through TCR register, you will set the value in PR register. PR value will determine the time resolution, that after how long your TC value will be incremented. So PR will decide that. So in this case, we will make it 0. So if you will make it 0, so after every clock cycle, every PCLK cycle, you will find the increment in TC if our PR value is 0. Once you have configured that, then configure MCR register, that after match, what exactly you want to do. Most of the time, we want to reset the value. So if you have to reset the value corresponding to the match register, so if you are using match register 0, so match register 0, 0, 1, 2. So these in match register 0 MCR, in MCR. So if after match register 0 matching, we want to reset the value of TC, obviously we have to do that value, that operation also. So the first position should be 1. That will help system to understand that once your TC value will reach and match MR0 value, then it has to reset this. Then you will update the cycle time in MR0. So you have to write the complete cycle duration. Then you have to write in the corresponding match register the corresponding duty cycle, depending on what average voltage you're expecting out of that pin. So based on that, you have to write the value there in match registers. Match register 1 to 6 corresponding to 6 output pins. Then you have to enable the bit in LER bit, so that every time whenever you will introduce new value, your system would latch it to the shadow register. So for that purpose, you have to enable it through load enable register. And then in the corresponding PCR register, whether you want single hash, double hash, so that all you have to configure. And already through TCR, we have already configured PWM module, but later on it may be possible that out of the 6 channel signals, so you are interested only in some 1 or 2 channels, or maybe any channel you are interested in. So to enable that channel, specifically you have to mention one corresponding to its bit position in PCR register. That's all corresponding to the configuration of PWM.